Every time you stream a game at a local sports bar or, say, access a secure military network, you are actually relying on a microscopic beam of light hitting a tiny ceramic target.
Yeah, it's literally the backbone of the whole system.
Right. It's so easy to think of our data as just this wireless magic, but today we're doing a deep dive into the intensely physical foundation making it all happen.
And it is highly physical. I mean, we are looking at a very specific piece of hardware today.
Exactly. We're unpacking a highly technical spec sheet from HDTV Supply. We're looking at the Avenview FO-MMD-SC-SC-30 duplex fiber optic patch cable.
That's quite a mouthful.
It is, yeah. But we want to see how this roughly $157 100-foot cord acts as the totally invisible high-speed foundation for basically everything you do online.
It's honestly a brilliant testament to how demanding our everyday infrastructure has become. Like, if you really want to understand the speeds we expect today, you have to look inside the wire. You need to see how the data actually travels.
Okay, so let's look inside. The specs list this thing as a 501-to-5 OM3 aqua cable.
Right, which tells us a lot right off the bat.
Yeah, for those keeping track of the standards, that aqua jacket immediately tells you it's an OM3, meaning it's built for a massive 10 gigabit bandwidth. And inside, it has 50-micron core and a 125-micron cladding.
To kind of help you visualize that, a single human hair is roughly 70 microns.
Oh, wow, so it's really that small.
Yeah, thinner than a human hair. So the data is literally beaming through this glass core that is incredibly thin. And that 125-micron cladding, well, that's the outer optical layer. It basically acts like a mirror, right?
Yeah.
It traps the light inside that tiny core so it doesn't escape out the sides.
Since it's specifically a multimode cable, I always, I kind of picture it like bouncing several different colored flashlights down this perfectly mirrored microscopic hallway.
That is a great way to think about it. It lets multiple data streams travel simultaneously.
But taking that flashlight analogy a step further, the real physics challenge has to be keeping those light pulses distinct over a long distance, right?
Exactly. And that is where the laser optimization comes in. That 50-micron core is laser optimized for standard LEDs and VCSLs.
Right, VCSLs? What are those?
Yeah, they're vertical cavity surface emitting lasers. So essentially ultra-fast, highly focused light sources. The glass core itself is actually engineered with a graded index.
Like what, exactly?
Meaning it gently bends the light back toward the center rather than letting it just ricochet sharply off the edges. That's how it prevents those different, flashlights from bleeding into each other and smearing the data over a 100-foot run.
Okay, that makes sense. But keeping those lasers perfectly separated inside the cable doesn't really matter if the light scatters the second it hits a server port.
Oh, absolutely. The transition is everything.
Which brings us to the ends of the cable, right? The
Okay.
SC-to-SC connectors. The specs say they use 2.5mm ceramic ferrules, push-pull snap-in latches, and boast a tiny 0.25 decibel insertion loss.
Yeah, the connector is really where the battle for signal integrity is won or lost. That 0.25 decibel insertion loss, it basically means almost zero light is leaking when it bridges that physical gap from the cable to the machine.
I mean, with 10 gigabit speeds becoming the standard, I get the need for precision.
Yeah.
But I have to ask, why can't we just, twist fiber wires together with electrical tape like old copper speaker wire?
Oh, I mean, you would get zero signal. None.
Really? Just complete failure?
Yeah, you have to factor in the extreme fragility of light transmission. A microscopic misalignment causes catastrophic signal loss. And think about the reality of a bustling data center. Equipment gets upgraded, racks get moved, troubleshooting happens constantly.
So they're constantly being messed with.
Exactly. And if the connector housing wears down even a fraction of a millimeter after a dozen unplugs, the core misaligns. The light literally bounces off into the void. That's why they over-engineer them to survive 1,000 baiting cycles.
And that explains the ceramic ferrules too, right?
Yeah. Yes, exactly. Ceramic won't expand or contract with server room temperature swings. It ensures those pulses line up perfectly every single time it clicks into place.
Which makes complete sense when you look at how this is actually deployed in your physical environment. The duplex design uses the zip cord style.
Right, so a tech can easily just pull the two joined strands apart when routing them to different ports on a really dense switch.
Plus, the outer layer is an OFNR jacket, which stands for Optical Fiber Non-Conductive Riser.
Which is huge for safety.
Yeah, it means it doesn't contain electrically conductive elements. And more importantly, it actually complies with strict building fire codes. So it won't act like a flammable fuse running between floors inside a wall.
And because it arrives pre-terminated, those ceramic connectors permanently molded on at the factory, nobody is standing in a dark server room trying to hand splice microscopic
Yeah,
glass.
that sounds like a nightmare. So it's basically ready for active device termination in WANs or high-density Ethernet right out of the box.
Exactly. It drastically reduces labor costs while completely removing the margin for human error during these really complex
It's
installations.
just wild to think about. This single Avenview cable really represents the delicate, precision-engineered reality behind our incredibly fast-paced digital lives.
It truly is the highly physical thread making the whole wireless world possible.
Which leaves us with a final thought for you to mull over. Right now, your entire digital infrastructure relies on perfectly aligned pulses of light bouncing through 50-micron strands of glass. As our global data demands just continue to multiply exponentially, what happens to our communication networks when we inevitably outpace the physical limitations of transmitting light through solid matter?